Hello everyone, welcome to the final lecture of this week. We're going to be, again, I'll be live coding this particular lecture. And what I really want to do is kind of tour what the different capabilities of sklearn are. And in order to do that, I'm going to be pulling down different data sets and doing a lot of stuff on the fly. Sklearn is a fairly large library with many capabilities. It has terrific documentation. So this is a kind of typical page from the sklearn documentation. Not only does it give you a function signature and a nice summary of what the component does, along with kind of the usual explanation of parameters, but additionally, just about every object is included in a user guide that again gives code examples and a more in-depth discussion of what a particular object does. Sometimes this involves diagrams and plots. So the documentation is very thorough, and I definitely suggest that you have a look around. It's very nicely organized. If you go to their documentation page, they have tutorials, quick start guide, user guide, and each component of the documentation in the user guide is broken down by different kind of classes of model or tasks in machine learning. So, they have supervised learning models, explanations of all of these. I'm not going to talk about unsupervised learning. They, have model selection, which I'll be giving a lecture on next week. Transformations, which will be some among the things we talk about today, as well as a guide to datasets included in sklearn. So really great documentation. So let's get started. I'll make a new notebook, and again, just like the classification notebook, I'll be sharing this when I post the videos to the video downloads folder later today. So I'll make a new Python 2 notebook, and I'll just call this WQ sklearn. So first, let's get some data. So not quite the right thing. Fetch California. Oh, right. We don't use that in this. We use it in intro ML. There we go. Fetch California housing. Oh, from sklearn.datasets, of course. So I'll be first working again with the California housing dataset. In case you forgot, yes, we'll need pandas. So in case you forgot, the California housing dataset has about 20,000 observations on 8 different predictor variables or features, and then of course it also has labels, which are the median home price in each region in this table. So each of these rows corresponds with a region in California. Each of these rows corresponds with the same region of California. And those are the median home prices in those regions, maybe expressed in hundreds of thousands of dollars. I don't really know. Okay, so if we wanted to start working, we've worked with this data before, but one thing we may want to consider is when we actually look at the scatter of the data, say for median income versus the home prices, this data has a particular scale. The median incomes range from, down by about 0.25 all the way up to above 14. And if we were fitting a linear model to this data, that's going to have the form f of x equals beta 1 x 1 plus beta 2 x 2, and so on and so forth. Maybe with a beta 0 here. And we might want to interpret the results of this model to pick out what components of the features, which features are most impactful on the median home price, which features are most important for predicting the median home price. And if I just looking at this plot, if I were to draw a line, a best fit line kind of just by eye, I would see that over the space from 2 to 4, I would probably go from about maybe here up to about here. So I would make a change of about 1 in vertical distance for a change of about 2 in horizontal distance. In other words, I would expect a slope of about 1/2 against this feature. So if median income is feature x1, then beta 1 would have a value of about 1/2. And beta 2 would have a value that depends on the scatter of the data for x2. We minimize all of these simultaneously, so actually it depends on all the features simultaneously. Nonetheless, you get the idea. The different features might have essentially different slopes when plotted against the median home price. But that slope itself depends on the scale of the feature. If instead of measuring median income in these units, I measured them in, say this is in maybe tens of thousands of dollars. If instead I measured these median incomes in thousands of dollars instead of tens of thousands, then this would be 20 and this would be 40. I would still only see an increase of 1, but now instead of being over a distance of 2, it would be over a distance of 20. So my slope wouldn't be 1/2, but rather 0.05. So the values of the different betas depend on the units we use to measure these features. In other words, it depends on their scale. Now, say we want to compare different features. In order to compare the different features, we might say, oh, well, in order to compare them, I know they need to have the same units. I can't say if I have, 2 oranges, or 2 kilograms, say, of something, and I have, let's say I have 2 kilograms of, apples, and I have 20 centimeters of thread. Which do I have more of? Well, then I'm asking, is like 2 kilograms greater than 20 centimeters? But that's not a sensible question. To compare 2 quantities, they must have the same units. So maybe I take my thread and I put it on a scale, and I find, okay, now I have 2 kilograms of apples, and 20 centimeters of thread turns out to be, say, 10 grams of thread. So now I ask, well, is 2 kilograms of apples greater than 10 grams of thread? This is still not a sensible question. In order to answer, I have to know what a typical amount of apples to have is, and what a typical amount of thread is. Whenever we want to compare 2 different quantities, or quantities of different things that come from different contexts, we'll want to compare them by z-score. Or that's kind of usually the way, so, okay, maybe the better way to say this is like, whenever we want to compare quantities of two different things, or from two different contexts, we need to non-dimensionalize the quantities. This is similar. This is what we do when we compute z-scores. So if you're not familiar with z-scores, they show up in the DW mini project, and there is some discussion about them on the message board. So maybe I'll actually link to my post on the message board about z-scores. So instead of comparing 2 kilograms of apples to 10 grams of thread, we should first account for the difference in means and variances between the two contexts. Instead, we'll compare the quantities let's see, how shall I do this? LaTeX, tilde, wide tilde. That works. So instead what we'll do is we'll subtract off the mean from the measurement and divide by the variance, or the standard deviation rather. So we would first look at the mean kilograms of apples in our sample and the standard deviation of amount of apples in our sample, and likewise for thread. And we would non-dimensionalize those quantities by subtracting off the mean and dividing by that standard deviation. And so then we could compare these two things. So for example, to carry on with the apples and thread, so we have our 2 kilograms of apples, we subtract off the mean, we divide by the standard deviation. We have our 10 grams of thread, we subtract off the mean and divide by the standard deviation. So over on this side we have 1, and over on this side we have 2.5. So because once we account for the different scales applying to the different contexts of apples and thread, we find 10 grams of thread is actually more than 2 kilograms of apples, in that it is a more extreme quantity of thread it is unusual to have 10 grams of thread when the mean is 5 grams and the standard deviation is 2 grams than 2 kilograms of apples. So all of this is to motivate the idea that often when we do linear regression, we'll want to normalize the features in our feature matrix. We'll want to put them all on the same scale. And what that will let us do is once we fit our linear model, we will be able to use the coefficients as measures of how much each feature contributes to the final prediction. We put all the features on the same scale by making them dimensionless quantities, and then we can compare their coefficients to get an idea of which features are most important. And in sklearn, the way that we can do this is using the standard scalar. So the standard scalar is part of the pre-processing module, and it standardizes features by removing the mean and scaling to unit variance. And this is the first example we've encountered, I believe, of what I would call, or what sklearn calls, a transformer. So I can take my scalar and fit it to the data, and what's happening when I fit it to the data is for each column, it's computing that column's mean and standard deviation. And then I can take that scalar and transform my data frame, and what happens is it subtracts off the mean and divides by the standard deviation column by column. So if we look at the transformed data frame compared to the original, we see the median income has shifted down. We even see negative values. And that's because all of these columns must have zero mean. So they must have values that fall on the negative side and the positive side. It doesn't make sense to have negative population, of course. But what we've done is we've put all the features on the same scale. So maybe I'll call this tally df trans for transform. Oops, I don't want head here. There we go. So here I'm just plotting two variables, two features. We see median income. It's skewed. There's a larger reach on the positive side, but the mean sits here at 0. And maybe what I should do instead, actually, is look at some histograms. So population and median income are both skewed. Median income somewhat less so. But we can see there's, for the most part, a pretty nice bell shape here from -2 to 2. And the mean, even with this skewness, sits right at 0. And the data falls off about half the height over a width of about 1 in either direction. So the data has been rescaled to have a mean of 0 and a standard deviation of 1. And likewise with the population, it's harder to see because it's so skewed. Maybe what I can do here is population less than 10 tally df. And this will just help us see a little bit better. So again, it falls off about half of its height over a width of about 1. And the peak is to the left of 0, but since it's so heavily skewed to the right, the mean is indeed 0. And we can also see that by looking at the mean of each column. And we see all of these are to the minus 16th or 17th power. These are incredibly small numbers, very close to 0. And if we look at the standard deviation, we find it's very close to 1 for all of them. These are just basically coming down to floating point rounding errors, these differences from 0. So the standard scalar is one of the simpler transformers, and it's very common to use. Now, we might take this transform data and then fit a linear model to it. And then we have our model, which has an R squared of 0.606. Now, I'm not going to get a different R squared than if I fit to the untransformed data. I get the exact same R squared. This does not improve the performant. The scalar does not improve the goodness of fit of the model. But what it does is, if I am fitting to the transform data, so I'll call this second model. We'll make a second model that gets fit to the untransformed data. We'll call that model 2. The model fit to the transformed data, I can compare these coefficients and pick out, what are the most influential features on the prediction. And that'll simply be the largest ones. The bigger in absolute value a particular coefficient is, the more strongly the model responds to that feature, right? So if one of these coefficients in my model is 0, that means that feature doesn't contribute at all, because that feature is being multiplied by 0. If, on the other hand, this coefficient is large, that means this feature has a large impact on, positive or negative, on the predicted value. So the first feature and the last two seem to be most influential, while these two features are not very influential. So median income and the geography are pretty influential, while average occupancy and population are not. And that matches our intuition when we plot, for example, the population against our target variable. There's not really a noticeable trend here. Even more so with average occupation, which is a little easier to see as long as I do some filtering. So let's consider average occupancy less than 10. Why didn't this work? Must have the same dimension, of course. There we go. So this just looks more or less like random scatter. There's not, I could maybe imagine fitting some kind of curve that comes down this way, but there's not a lot of pattern to this data. There's not a very distinct trend going on here. And unsurprisingly, the coefficients are accordingly quite small. Another small one is house age. If we look at house age, we also see random scatter there. So there's not much impact of house age on the predicted values. If we look rather at the coefficients of model 2, this tells us much less, because the measurements are all on different scales. So here, for example, it looks like the most significant feature is average number of bedrooms. Average number of bedrooms actually has the highest coefficient. But if we were to plot average bedrooms, maybe with some filtering, so that we can see a little bit better. So maybe less than 5. Excuse me. We again see, something that looks essentially the same as when we plotted average occupancy. There's I could maybe imagine fitting some kind of curve that decays very sharply and then plateaus out to 0 here. But if I were just fitting a line, I wouldn't really know where to put that line. I would give it a very small slope, probably along here or something like that. There's not much of a linear trend going on here. And once we account for the scale, this particular feature, it has some slope, but not as large as these other features. It definitely does not have the largest slope. So if we want to inspect our model and get out kind of the importance of the various features, then we need to use this scalar. Just checking on time here. Good, I have plenty of time left. So scaling is not the only transformation that we ever want to do. In fact, if you look at pre-processing, there's many other transformers in the preprocessor. There's the polynomial features transformer, which will allow us to fit polynomials to our data. By what we would do is we fit a linear model, but we compute polynomial terms between the features we have. So if we wanted to fit a parabola, a second degree polynomial, to our data, and we have the features a and b, polynomial features is going to compute a squared, a times b, and b squared for us, and then a polynomial model, if I have a second degree polynomial model, if I have features, say we have features x1 and x2, a second degree polynomial model is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2 plus beta 4 x1 squared plus beta 5 x2 squared. And you can see here, this model, we have polynomial combinations of the features, but the model is linear in the coefficients. The coefficients are not raised to any powers. So we can fit a linear model just calling each of these features some kind of new feature. So, for example, let x3 equal x1, x2, x4 equal x1 squared, and x5 equal x2 squared. Then we have just copy this. So you can see, if we define x3, x4, and x5 in these ways, we end up with something that looks exactly like what we had before. This is just a linear model. So, we could also, say, take our scaled features, and transform them using the polynomial features transformer. Now, for the scalar, the standard scalar, before I transformed the data, before I could use scalar.transform, I had to fit it. And that's because in order to perform the transformation, this transformer had to know something about each feature. It had to know the mean and the standard deviation. So the fit step computed those quantities. If I were to try to transform, let's see. Oh, I didn't use unfit scalar, I used scalar. There we go. If I try to use a scalar that hasn't been fitted, and I try and use it to transform, I get this error, not fitted error. This standard scalar instance is not yet fitted. Call fit with appropriate arguments before using this method. So the scalar must know what the mean and standard deviation is of each feature before it can perform the transformation. And we calculate those things in the fitting step. However, polynomial features doesn't need to know those things. It's just computing these products. x1 times itself, x2 times itself, x1 times x2. There's no information about the data itself that this transformer needs in order to perform the transformation. It still gives me a not fitted error, however. To my surprise. Compute the number of output features. So it does need to know something. I would expect this to have been computed in the transform method, but apparently not. In any case, what I will show now is the fit transform method, which does both the fitting and transformation in one step. So this is equivalent to if I had just chained the transform method onto the fit method. In the class definition for polynomial features, or any transformer, in fact, that is the definition of the fit transform method, is exactly this. And I'll jump into that in depth a little bit later. Just checking time. There's 2 more topics I want to cover. So we can take these polynomial features and again fit a linear model. And we have a slightly higher R² now. So this model does a little bit better at predicting the values of median home price for each region based on the features we have. We would expect this for a few reasons. Most importantly, essentially being that we have given ourselves more degrees of freedom. We have a more complex model, so it can more accurately conform to the shape of the data. I'll talk a lot more about this next week when we talk about model selection and bias variance trade-off, which I introduced in a lecture this week, but we'll be talking about bias variance trade-off much more next week. So by now, we've done the following. We started with our Cali DF. And we made this Cali DF trans. Data frame. And then we made this Cali poly data frame. And then finally, we fit what we call the model to Cali poly. But this is like a lot of intermediate, it's a lot of intermediate data structures. You know, we started off with Cali DF, and then we made Cali DF trans, and then Cali poly. And secondly, even though this is the estimator, it's not really the whole story about what's in our model. Because if I was just looking at what the model object is, well, that's just this linear regressor. And so I might think that I have my model is a hyperplane. It's a flat surface. But it's not true because I have polynomial features, so I actually have a curved surface. My model is linear in the coefficients, but it's polynomial in the original features. So really what I should consider all of this to be my model. Everything that I do between the raw data and my predictions should rightly be considered to be my model. Now, I'll talk more about why that is in future lectures, but for now, I just ask you to accept that claim. You know, everything I do between my raw data and my prediction is my model. It represents all my choices I make for generating predictions from raw data, and we'll call that the model. But if that's the model, then it's split over many different Python objects. And I have like a bunch of lines of code and all these intermediate data structures to keep track of, and it's a bit of a mess, and it's only going to get worse as our models get more complex. So the next thing I want to introduce is an object called pipelines, which can package up these linear steps, or serial steps that take me from raw data to predictions at the end. So instead, what I'll call my model is a pipeline that contains a scalar, a polynomial feature generator, or transformer, and finally, the linear estimator. And now, I can take all of this and fit it directly to Kali data, or the Kali DF original features. And I get a value error because why? Operands could not be broadcast together with shapes. Kali DF. There we go. And what's happening is Kali DF, the features, get passed in, and when we fit our model, the standard scalar gets fit to the features, and the features get transformed. And those transformed features pass on to polynomial features, which also fits to the data that came out of the standard scalar and then transforms it, and that transformed data gets passed to the linear regression estimator. So each step is calling fit transform until the very last one, which is our estimator, which is not a transformer. So it doesn't have fit transform, it doesn't transform data, so it just gets fit. So we can fit all of these things simultaneously, and we don't create any intermediate data structures in some kind of throwaway variables. We can pass in just the original feature matrix, the raw data, and it gets transformed on the way to the estimator. So these are really handy. They plug in very nicely to a lot of the other tools in scikit-learn that we'll be exploring in next week's lectures. One thing I want to highlight is that these transformations are serial, meaning they happen one after another. There's also the possibility of doing parallel transformations or parallel processing using what's called a feature union, which I'm not going to explain now, but I will explain in a future lecture. But pipelines are very simple, very easy to use, and are very handy for packaging up all the steps of a model into one scikit-learn object. And I know I said I wanted to cover two more things, but I think I'm actually going, and I've only covered one of those two. I think at this point I'm actually going to shift gears and just highlight some things in the documentation. A lot of what remains in the machine learning lectures will be going into different components of scikit-learn in more depth. So don't worry, this is certainly not the last time we'll be exploring scikit-learn. Actually, I want to go to the user guide. One thing I want to highlight is there is a lot of transformers. We're not always working with a feature matrix right away. We don't always have a nice table full of numbers that we can use with some estimator. So there's all kinds of transformers for constructing feature matrices from things like text or images. So sometimes our raw data isn't numbers, it's text. Sometimes our raw data has a lot of features, many features, which can be difficult to work with for a number of reasons. Partly just because it can be very computationally intensive, but also it can add a lot of noise to our data, essentially. I'll be talking more about that in the future. So there's transformers that limit or reduce the number of features in a smart way. We call that dimensionality reduction, which again I'll be coming back to. Ways for reshaping kind of the feature space, the space that the features sit in, known as kernel approximation or the kernel trick. There's tools for picking the kind of like tuning our models, trying to change the structure of our models to be the best as it can be. We'll be going over that next week in the model selection lecture. Tools for model evaluation. And of course, the various kind of estimators themselves. Nearest neighbor models, support vector machines, linear models, all sorts of things. Decision trees, which we'll be talking more about soon. So there are a lot of components to scikit-learn. I definitely suggest that you dive into the user guide, read up about different estimators in the supervised learning section, different transformers in the dataset transformation section, as we are working with scikit-learn more in the future lectures. And I think since we're up at the hour, that's where I'm going to conclude this lecture with one more word, which is we will also be looking at one more element that I didn't get to today, which is defining our own custom estimators and transformers. So in addition to all the tools, ready-made tools that scikit-learn exposes for us, there's additionally a really nice set of base classes that scikit-learn provides that we can inherit from and extend to write our own custom scikit-learn estimators and transformers that plug in with things like pipelines and other pieces of the scikit-learn API seamlessly. So that's the last lecture for this week. And next week, we will be getting into a little bit more depth. There's only, I know, 2 more kind of notebooks, model selection and feature engineering in the module. But each of these notebooks starts to get into quite a bit more advanced topics, so we'll be spending multiple lectures on these notebooks. I would say also at this point, you are familiar enough with, or I hope you are familiar enough with sklearn and how the various components work. And between the examples that I've worked through in the notebooks thus far and by looking at the documentation, you should be able to start making headway on the ML mini project. So I would encourage you to at least start looking at the ML mini project and trying to work on that in addition to any other mini projects you might be working on. Or if you have finished the other ones, you should feel confident proceeding on to this one. And the ML mini project is the last mini project in the course. So I will be coming back with more lectures next week. See you.